Good afternoon. So today we'll be talking about intermediate code generation, and remember that it is not code generation; it is actually intermediate code generation. So if we look at it, underline this: it is intermediate code generation, right? Now, why do we want to generate intermediate code, not the target machine code? Because intermediate code is very similar to machine language code, but it is not exactly machine language code. It is more like, in fact, a little lesser than the assembly language code. So once we find out the intermediate code, we can easily convert it or convert them to the machine language code. Now, intermediate code, as it is going to be generated algorithmically, will contain lot of unoptimized code. We'll see that, and therefore optimizing the intermediate code is a lot easier compared to optimizing the target machine code. And the second benefit is that from the intermediate code we can actually generate machine code for different machines. So our compiler, as far as we have read, the lexical analyzer, the parser, and this intermediate code generator, they belong to the front end of the compiler, and once this front end completes, then we go to the back end of the compiler. The front end of the compiler does not change depending on the machine architecture, but the back end of the compiler will change depending on the machine architecture, and therefore compiler as such is a system software. Let us go to the details of this intermediate code. What could be these intermediate code representations? There are many types of intermediate code representations. It could be graphical representations like abstract syntax tree. It could be a postfix notation, but we will dwell on three address code, particularly the quads. Three address code, as the name suggests, it has at most three addresses. So, for example, if I have two operands y and z and then opcode, then the result of executing the opcode on the arguments y and z, the result x is obtained and the result is assigned to x. So that is known as three address code. We'll discuss in detail about this three address code in the entire slide presentation for today. We also have two address code which we will not use, which is like two addresses will be allowed at the most, and the result is x. One of the argument will be x, and the other argument will be y. So if it is written as x assigned of y, basically you have to read it like x assigned x of y, meaning the operation will be executed on two arguments, two operands, x and y, and the result will be stored back in x. So let us go into some details of three address statements. For example, the assignment statements could be examples of three address codes like x is y of z, this is the one, or copy statements, that is assign the value of y to x, that is the second one, and conditional jumps go to some label, conditional jump if x del of y go to some label, function calls, you define a number of parameters like param x, param y, param z kind of thing, and then call the procedure p, supplying it the number of parameters that were specified before this call. We also can have indexed assignments. You just see that in three address code, you cannot use multiple dimensional arrays. So, for example, if y is an address, then I is the index is an address. So these are the two addresses already done, and this is the third address. So if I have multi-dimensional arrays, we have to convert it to a single dimensional array and only then the arrays can be manipulated. Again, we'll look at them in detail in later part of our lecture, not today. Also, we have pointer assignments and many other kind of statements. But firstly, the arithmetic expressions and assignment statements, primarily the arithmetic expressions. Let us look at some more examples of three address code. See that in this particular code, how many addresses are used? 1, 2, 3, 4, and 5. So this is not in three address code. If I want to make it three address code, then we have to introduce temporary variables like T1, which is assigned to minus C, then T2 assigned to B into T1, T3 assigned to minus C, T4 assigned to B into T3, then T5 assigned to T2 plus T4, and A is assigned to T5. Also see that this T1, T2 and T3, T4 are the same thing. So as I said, since this particular code will be generated by algorithm, such this is the same as this. So possibly we could simply say that T5 is T2 plus T2, right? But since it is generated algorithmically by an algorithm, therefore such an unoptimized code will be generated, and that will be optimized by some other algorithms which we'll talk about. And that is one good thing about this three address code, that it can be optimized very easily compared to the target machine code. If we go to three address code for logical and relational expressions, this is the first one is a relational expression A or B and not C. As we know that the precedence of not is the highest here, so first we do not C and put it in a Boolean variable T1. Then the next one is B and T1 and we put it in T2, and then A or T2 is this T3, and the result of this entire expression is stored in T3. In fact, in this case, we found out that this three address code is generated by introducing Boolean variables. We can also avoid using Boolean variables by conditional and unconditional jumps, which we'll be talking in detail in another lecture period, not today. Just today we're giving some examples. The second example is going to give you some idea about that one. See, A less than B. So what we do is, if A less than B, go to L1 and go to L2. Now what is L1 we do not know, what is L2 we do not know. So this expression has to remember two labels. One label is the label where control should go in case this particular expression is evaluated to be true, which we call true exit, and another one is false exit, that is the target level where control should go in case this particular A less than B is evaluated to false. More on this will be discussed in complete detail in the next video recording. So for today, this is enough to know about the three address code for logical and relational expressions. Next, let us see, if I have a function called like foo a plus 1 comma b comma 7, that is, we are calling a function foo with three arguments. The first argument is a plus 1, the second argument is b, and the third argument is c7. Then the way we kind of translate this into three address code is this: T1 is assigned a plus 1, T2 is assigned 7, then parameter T1, which is the first parameter, param B is the second parameter, param T2, which is 7, is the third parameter, and then we do call F3, that is the third parameter. So this is what is meant by the three address code of translating procedure calls. So I just wanted to give you an idea of what three address codes are, some examples of three address codes from various different constructs of programming languages. There are many others which we will deal with in successive video lectures. But today, for that matter, we'll talk about primarily three address codes for arithmetic expressions. Before we proceed to the arithmetic expression part, let us see that there is a beauty about this three address code, which says that I can think about three address code as lines or as an array of quadruples. I mean an array of structure where the structure contains four uh, components. One component is the result, where the result is stored. The other two components are arg1 and arg2, the operands, and the fourth component is OR. So if we assume that, then the entire program may be considered to be an array of quadruples instead of an array of an array of strings written in a file. So this sometimes is handy in order to rearrange the code for global optimizations. And however, thread-based code, as I have said, has a cons, has a disadvantage of using too many temporaries. Now, naturally, too many temporaries, that is because, after all, in one particular instruction, you cannot have more than three addresses. You can at most use only three addresses. So now this is time to change gear and look into the detail of the three address code in operation. In particular, we look at this grammar: E produces E plus E, or E produces E star E, or E produces number. A very simplified grammar of arithmetic expressions and ambiguous grammar of arithmetic expressions. We will not talk about the ambiguity now, because our challenge is creating, evaluating the expression, not in creating the parse tree. We'll assume that our parser is kind of, sufficiently intelligent, and therefore it could create the correct parse tree depending on the precedence of the operators plus and star. For example, if 9 plus 2 star 3 is the operator, then the parse tree that I have given here is the correct parse tree. It is, if we look at it, it creates the, 2 plus 3, it evaluates at first, and then the evaluation is added to E, and we get the result back in the root. Now, if this is the parse tree that is correct for 9 plus 2 star 3, we should be able to say in what order the reductions took place. Now, the reduction, when I say reduction, you must understand, we talked about LR0 parser, we talked about LR1 parser, we talked about bottom-up parser in general. And in bottom-up parsers, the technique basically believes in handle reduction. So therefore, in this 9 plus 2 star 3, there must be a handle. And what is the handle? If I am given the parse tree, what is the handle? What you can do, you can read the tree in an in order fashion, and from left to right you read. So the first opportunity where for example here, if I look at it from in order, then this is the first thing that I can see, and therefore this is where the first reduction took place. So let us look at it in detail in the next slide. See, for example, this is the first reduction which took place. Now, what was the rule that was used? The rule that was used is E produces number, and the number was 9, and therefore this E produces this number. This is reduced. The parse tree is also reduced, and the resultant parse tree looks like the parse tree that I'm showing now. But remember that we are now evaluating the particular expression. Now, if this is the tree after deduction, then I forgot about what was beneath this particular non-terminal. What was beneath this particular non-terminal? If beneath this non-terminal was the number 9. Now, therefore, we have forgotten that number 9, and which we cannot forget, because if we forget them, then parsing can be done, but evaluation of the expression or code generation from the expression, that cannot be done. So we must not forget our the tree that I reduce. I must remember the tree that I reduce. How to remember that? Understand that each node in this parser, this one, each one of them is a node. Every node has a number of children, and I can have, when I write this grammar, I can have more attributes to the non-terminals. Now, if I say that one non-terminal should have a particular attribute, then all non-terminals will have that attribute. How do I reset that attribute is up to us. So, for example, let us assume that we are adding an attribute val to the nodes for E. So, every node E in this parse tree contains an attribute val. Now, just see that I have to remember here that E dot val is 9. Why? Because I remember the value that was obtained in this parse tree, in the parse tree that is below this particular non-terminal. The value generated here should be remembered here. So whenever I use this rule, E produces number, I should have one more action with this rule. So the parser, when it reduces using this rule, must also execute this particular statement. And what is this statement? E dot val is equal to number. So by the value of number, it is assigning the val field or attribute of the non-terminal E. So the parser executes this action during reduction. If it does that, then naturally E dot val becomes 9. What is the next reduction? Again, look at the tree kind of, in an in order manner, and I can find out that this is the next opportunity to reduce. And you are right, this is the next opportunity to reduce. So I reduce here. And we know that if we are reducing by this particular rule, then this is the action that I must take. So if I use this rule to reduce it here, right? To reduce it here, then I also have to execute this particular statement, and therefore, as I said, that this is the rule used here. The action taken is this, and therefore E dot val is equal to 2. Now the next reduction will be here, because again you look at the tree, and in order manner you'll find out that this is where the reduction can take place. Right? It is very easy from the bottom. Look from left to right actually, and you should be able to find out where the next reduction takes place. So again, the same action has to be taken. Why? Because what action will be taken does not depend on where you are in the parse tree, but depends on what is the rule that the person uses for reduction. Because if a rule number 3 is used, always the same action will be taken. So here, therefore, after this action is taken, E dot val will be 3. Now again, if we look at the parse tree, this is the part which will be reduced, right? This is the part which will be reduced. Now, what is the rule that you use to reduce it? E produces E star E. Now I have to distinguish between this E1 and E2. Why? Because this E1 has a value of 2, this E1, E2 has a value of 3. And what is the semantic action that I need to take here? I have to put some value in this E, right? So what is this E dot val? Understandably, this E dot val is this value multiplied by this value, and exactly that has been written here. So once I execute that particular statement, I come to E dot val is equal to 15, is equal to 6. And now this is my reduction, my last reduction in this parse tree. And what did I do here? I did E produces E plus C. Now naturally, this is my E1. I distinguish them by E1 and E2. And the action taken is E1 dot val plus E2 dot val, that is 9 plus 6, and that is 15. And I put that 15 here. And that gives me the expression as E dot val. So at the root, the value of that non-terminal gives me the value of the resultant arithmetic expression. Now that sounds okay, but now we know that after all, we are not generating the value when I do a compilation. When I compile, actually I have to generate a code. I mean, given the high-level language code, I have to generate the 3 address code. So for example, if this is my uh, arithmetic expression, then the code that I have to generate is like this. T1 is 9, T2 is 2, T3 is 3, T4 is equal to T2 into T3, and T5 is equal to T1 plus T4. So this code has to be generated when I traverse the parse tree and reduce the handles or prune the handles. So again, what is the technique there? The technique therefore is associate add attributes. Attributes to E or the non-terminals, and to add actions to production rules. These are the two things that I need to do to uh, generate the three address codes. Let us have a bit deeper look into this particular code, and we will get two very important points. One is, see, we need to generate T1, T2. So I have to have a factory kind of a thing so that new temporary variables can be created. And we assume that we have a function called like new temp, which gives me a string standing for a new temporary variable. And we need to create and write quadruples. So I use something like this function emit. In emit, I write down the result, the the name for the result, the name of the variable for the result, the name of the variable for the arg1, the name of the variable for the arg2, and the operator which is to be operated on this arg1 and arg2. So for example, if I want to write t5 equal to t1, if I want to write this line, then the emit function will be called by t5, that's the result, t1 and t4, these are the two arguments, and plus, that is my opcode or operation. So these two functions will be using while writing the three address codes during reduction. So our actions for the non-terminals will involve function calls to these new functions, new temp and emit. So let us have a closer look to that. See the same parse tree and the same sequence of reduction. So this is the first reduction. And the rule used is if produces number. And what I need is I need to generate this line. Now to generate this line, first I need to create a new variable by a new temp. I add an attribute in E naming place. So E dot place is new temp and image E dot place comma number, right? So in this case, we have only see, we have 4 arguments here, but here I have only 2 arguments, which is quite normal. Quite normal because this says that in this particular sentence, in this particular quadruple, we are not using 3 addresses. 3 address does not mean that I have to use 3 addresses always. 3 addresses means 3 address codes mean I cannot use more than 3 addresses, but I can always use less than 3 addresses, even 2 addresses. For example, here 2 addresses are given. So this is the result and this is the argument. Since only one argument is there, no operation is needed. So therefore, here this emit basically means the result is assigned the number. So this line will be generated when the previous reduction took place, and next reduction naturally is this. Again the same same two semantic actions will be taking place. Now once this particular semantic action will be taking place, T2 will be generated, and once this emit will be taking place, a line something like this will be generated, which you can see now. So T1 is 9 and T2 is T2. To understand that, maybe there is a huge parse tree under this e dot place, and you have written probably 10 lines of code, 10 lines of code for this particular parse tree. Fine, you may do that. But where is the result stored? The result is stored is T1. So what it says is, whatever you have done so far, whatever be your code, how much code you have done, the ultimate result of that code is kept in a variable called T1, and that is available in the in the value of the attribute of the non-terminal E. So E dot place is the variable name that contains the result of all that you have done in the parse tree beneath that particular node. So for example, in this case, E dot, I mean, once I do that, E dot place is T2, and you see that T2 contains the result of all everything that you have done here. For example, now E dot place will be T3 because of this new temp, and after this emit, this particular line will be emitted, and you can see that this part of the computation is remembered in T2, this part of the computation is remembered in T3, and a new rule and a new semantic action. New semantic action means this is the emit which has completely result argument 1 of code argument 2, right? And the moment you do that, you have T4 equal to T2 into T3. And you see T4 is remembered in E dot place. So all this computation, the result is here, right? So once we are here, we'll forget everything. We'll forget the entire parse tree beneath this particular non-terminal E. But we remember that whatever we have written down as the shared address code, the final result of that is remembered in T4. Very interesting, isn't it? And then if I finally reduce this much, then I get again another. Sorry, this is with plus. This is with plus, and this is also this is with plus. Sorry for that. And uh, see here, we are not actually generating any. We are not generating any. We are not generating any value. Rather than that, we are printing the code. So here again, the same mistake actually is there. This is plus, and similarly, the rule used is plus. Sorry for that. So that is, I think, that is all that we had to talk about today. So you see, this entire code is written for that particular expression, and the final result is obtained at T5, which I remember. And maybe this E dot place is a part of a bigger subtree, right? So this T5 will be used to remember all that we have done here, and with that we go on parsing the other part of the tree, and we can do whatever we feel like. So, in a nutshell, therefore, the syntax-directed translation of expressions is something like this. If this is my grammar, then I mean we have already explained all that except this E produces ID. Now we can understand that this is my table. This table pointer points my symbol table. So I look up in the symbol table. If this ID is there, then the particular that particular index will be returned. I mean, in the symbol table with the name of the ID, if I search, then maybe it is available. If it is not available, uh, uh, then that should not happen. Actually, I mean that should not happen, and should that this else is not there. E dot place is ID dot place. So ID dot place is basically the symbol table entry for that, and then E dot place is that actually. So we'll look at this. We'll look at this particular semantic action in detail when we talk about uh, code generation or translation for declarations. Like you write int a comma b comma c. So at that time the symbol table will be generated, right? So that would be a very nice exercise for us we'll look at that at point of time. So for today, the study was primarily the syntax directed translation of expressions, arithmetic expressions. So we talked about, in summary, we talked about what is a three-address code, different examples of three-address codes. We also looked at how to evaluate expressions using syntax-directed translation. We also found out how to generate the code, three-address code for arithmetic expressions, and the whole story can be summarized in a few bullets. One bullet is find out the grammar first, and then find out the attributes that are needed in the non-terminals. And third bullet is attach semantic actions to each and every production rule. Now, how to find out these rules, how to find out these actions, how to find out the attributes. What you do, you take an example, draw the parse tree, and find out the sequence of reductions. When you look at the sequence of reductions, you try to find out what needs to be remembered in the parent node so that the children can be forgotten, right? What are the informations that you need to preserve in the parent, in the parse tree, so that after reduction the children will be forgotten, but the necessary elements that is to be remembered will be remembered, and the necessary prints that are going to be done, that will also be done. So you have to run an example, then only you can find out what are the attributes needed for the non-terminals and what are the semantic actions that you need to attach for the rules, for the production rules, right? With the example, when you take when you play around a little, then you can settle down. So these are the actions that I need for the production rules, and these are the attributes that I need for the non-terminals. Please note that the parser will execute the semantic actions when a reduction using that rule takes place, right? Right. So semantic actions will not be invoked by anybody else other than the parser, and when a particular rule is used to reduce, then then the semantic actions attached to that particular rule are are executed, right? And every non-terminal in the parse tree is a separate instance of a class or a structure in which you are adding some attributes by saying that I need these attributes. If you ever use yet another compiler yet, or Bison for that matter, which is a popular name for implementation of Yak on Linux. Now, there you will find out that you have a provision to add um, attributes to the terminals and attach semantic actions to the production rules. And then if you run your compiled part of code on the input, then you will find out the output is according to what you wrote in your semantic actions, right? So today this much was the target to be told to you. I hope that you have enjoyed the session. You could understand the basics of uh, three-address code and syntax-directed translation. We'll come back tomorrow again with another lecture video in which we'll be translating Boolean expressions and relational expressions. Thank you very much.